Hello everyone, this is Mr. Bowman and I am going to get things started with chapter 1 here in pre-calculus. Take note, we are not starting with section 1.1, we're starting with section 1.2. And in this video we are going to talk about the idea of relations and functions and domain. So as it says here in part 1, we've got two sets of pairings, set Q and set T. We are going to refer to the left-hand side of these pairings as the inputs and the right-hand side as the outputs. So we'll do the same thing and labeling that for set T. And what we want to start out with is listing all XY pairings for each set. So we'll do set Q together, and then I want you to pause the video and do set T on your own. So set Q, the XY pairings go like this. X2 is paired with Y2. X1 is paired with Y1. X3 is paired with Y3. And X4 is also paired with Y3. So pause the video and do the same thing for set T. So you may notice some similarities between these pairings, and you might also notice some differences. Set Q has 4 pairings and set T has 5. And we want to focus on some of their similarities and then take a look at their differences. So the first question we want to answer is, which of these sets has pairings so that each X value is paired with at least one Y value? Pause the video for a moment and see if you can answer that question. So the answer to that first question is both. Every X value in the input for set Q is paired with at least one Y value in the output, and the same is true for set T. The next question may seem very similar, but I want you again to pause the video and think about what your answer to this is. Which of these sets has pairings so that each X value is paired with a unique Y value? Another way of saying a unique Y value is just one Y value. So set Q, each X value is paired with only one Y value. Even though X3 and X4 are both paired with Y3, each of them, X3 is paired with one Y value, X4 is paired with one Y value. Compare that to set T, where X1 is paired with Y1 and X1 is paired with Y3. So the answer to that question is only set Q. So you might be asking yourself at this point, what does this have to do with what we're studying? Well, it's actually a very important aspect of mathematics, and both sets Q and T have a similarity such that each X value is assigned to at least one Y value. We call that a relation. On the other hand, if we have a set like set Q where each X value is assigned to a unique Y value, we call that a function. So set Q represents a function. Sets Q and T are relations. So all functions are a form of a relation. Not all relations are functions. So what we want to do next is we want to think about this in terms of points in a Cartesian plane. Points in a Cartesian plane are specified by an X value and a Y value. And that means we can graph relations and functions in a Cartesian plane. So what I'd like you to do right now is think about those two definitions, a relation and a function, And as you look at these three graphs here, determine which of the three is not a function, and see if you can think of an easy way to test a graph to determine whether or not the relation is a function. Go ahead and pause the video here and see if you can determine which of the three graphs represent a relation that is not a function. So if you said graph number 3, or the one on the right, you are correct. And there's an easy way to test a graph to determine whether or not it's a function. And it goes like this. Some of you may already know it. It's called the vertical line test. And if you can draw a vertical line anywhere on the graph and it crosses the graph at more than one point, that relation is not a function. That is impossible to do with the graph on the left. It's impossible to do with the graph on the right, or in the middle, but it's not impossible on the left. You can pick many places where you can draw vertical lines, and that vertical line passes through the graph of the relation in more than one place. And what that means is that all these points on this vertical line have the same x value, but they're also paired with multiple y values. So it's a relation but not a function. Now that you know how to determine whether or not the graph of a relation is a function, I want you to take a look at these 4 examples of tables of values. And you may have to think about plotting these as points in a graph and determine which of these relations is not a function. So pause the video and figure out which of these 4 are not functions. So if you answered letter D is a relation and not a function, then you are correct. I want to take a minute and go over some of these others, some of the points that often throw people. So in B, for example, x value 6 is paired with y value 13, and x value 7 is paired with y value 13. Those two x's are paired with the same y value, but each x value is only paired with one y value, so it's a function. In letter C, we see the pairs 2, 5 and 2, 5 show up twice. Well, 2 is always paired with 5 though, so it's an x value paired with a unique y value. It's still a function. In letter D, there are multiple examples of why it's not a function, so I just picked one. X value 4 is paired with y value -2, but x value 4 is also paired with y value 2, so it's a relation but not a function. Part 4 of this video gives you some relations that you're supposed to determine whether or not they're functions, and if they're not functions, give examples of why. So you might think of these in terms of graphing, and that's a great way to do it. If you can graph them and they pass the vertical line test, then they're a function. If they don't, then they're not. But if they fail the vertical line test, then we should be able to give some examples of x values that are paired with more than one y value. So the way I like to approach these is by solving each of these for y if it's already not solved for y, and see if I plug an x value in, can I get more than one y value. So as an example, if I were to solve this first equation for y, I would take the square root of both sides and I would get plus or minus the square root of x. So if I were to plug in an x value of 4, I could get a y value of 2, or if I plugged in an x value of 4, I can get a y value of -2. So this is not a function. Skipping over to letter B, if we were to solve for y, we would get y is equal to 5x plus 15. As you know, that's a graph of a line with a positive slope and a positive y-intercept, and therefore that passes the vertical line test, so this is a function. Letter C, well, this goes back to what we just finished in chapter P, solving absolute value inequalities, And we would translate that statement into y is equal to the opposite of x plus 7, or y is equal to x plus 7. That's how we solve absolute value or equations. So let's plug in an x value. I don't know, pick 3. 3 plus 7 is 10, so y would be equal to negative 10, or y is equal to positive 10. So in that case, an x value of 3 is paired with a y value of negative 10, or an x value of 3 is paired with a y value of positive 10. So C is not a function. Moving on to D, if we were to solve D for y, I would subtract 7 from both sides and add y to both sides, and we would get x squared plus 7 is equal to y, and you probably recognize that as a parabola that opens up, and any vertical parabola opening up or down is going to pass the vertical line test, and therefore it is a function. Letter E, on the other hand, you may or may not recognize that. So if you do, that is a circle with a center at the origin and a radius of 3. Well, imagine graphing a circle. It fails the vertical line test. But if you don't recognize that, you can always solve it for y. So y squared is equal to 9 minus x squared. And now you have to take the square root of both sides. So you have plus or minus the square root of 9 minus x squared. And as you can imagine, if you plug an x value in there, you will get 2 possible y values in there. So this letter E is not a function. And then the last one, letter Y, well, we've already solved for y, or letter F, I'm sorry. We've already solved for y here. Pick a number like 2, and if you plug a 2 in for x, you get a 5 for y, or if you plug a 2 in for x, you get a negative 1. So an x value of 2 is not paired with a unique y value, so it is not a function either. The only two of those that are functions are letters B and E. So we are going to finish up our video today by talking about the domain of a function. And the domain of a function is the set of all input, typically x values, of a function. So what we want to do is we want to take a look at these graphs, and we want to, from these graphs, determine the domain of these functions in interval notation. And if you want, you can verify that all of these relations pass the vertical line test and are therefore functions. A few notes here. We are going to assume, for example, that when a graph stops there in the middle of the window, that it literally stops, and that at the edge it continues on, because our graphs don't show that. So the domain is the set of all input, or x values. So what we have to do to determine the domain is look at over what range of, or over what set, I don't want to use the word range, over what set of x values does the graph exist. And in this case, this first graph exists on the interval from -3 to positive infinity. The x values go from -3 here all the way out to positive infinity without interruption. To the right of that, in keeping with our convention, our graph, we are going to assume, stops here but continues in this direction. So the domain is the set of all x values. Again, the x values in this example go from, on the left, -1, and on the right, if we assume that this keeps going, the x values are going to slowly approach positive infinity. So our domain here is from -1 to positive infinity. Remember, domains are x values. So what I would like you to do with the next four, well, let's say the next two, pause the video with the next two and determine their domains. If you said negative infinity to positive infinity for both, you are correct. The one on the right might give you a little bit of trouble because it looks like on the left hand side the graph is straightening up, but it is straightening up, but it continues to go out there towards negative infinity in the horizontal direction. Now let's take a look at a couple of more challenging examples. The graph on the left is called a step function, and again we're going to assume that it continues on in this pattern forever. And so if we start at the left hand side, it's negative infinity, and we never include infinities, and we're going to assume that the x values don't skip. In other words, if we were to do a vertical line test right here, we're going to hit the graph either here or here, but not both. So it's hard to tell in its current format, but we'll assume that the graph looks more like this. So open circle here, closed circle here, open circle here, closed circle here. So each x value is paired with a unique y value. So we're assuming we meet the vertical line test there. Now what we want to do is think about all the x values that we could put into this function. Well, basically, if we draw a vertical line anywhere, we're going to have a line that hits the graph. So again, the domain is from negative infinity to positive infinity. And now the last one. Again, arrow here, arrow here. Oh no, no arrow there. My apologies. Solid circle there. So our domain, our set of input or x values, is going to go from negative infinity to positive 2 is where the graph has this discontinuity, and the function does not exist up there at that open circle, but it does down here. So we don't technically skip over an x value of 2. It goes on to 3, it goes on to 4, it stops at 5. So our domain for this function is from negative infinity to 5. That's it for now with this video. In the next video, we're going to come back and we're going to talk about finding domains. We're going to review finding them graphically, and we're going to talk about finding them algebraically.